So size and scale is the first off. Normally I write that down, but you can't see it, so I'm not going to bother with it. The universe, of course, is a very big place. I can't describe how big it is, and that's the problem. Astronomers themselves can't really wrap their head around how big the universe is. So we develop a bag of tricks, again, a bag of tricks, to help us work from one scale to another in our heads. And if I say 10 gazillion kilometers, there's no way even an astronomer can imagine that. But we might, of course, gazillion's a made-up number, but if I gave you a real number, I might say, well, I know that's 10 times bigger than a galaxy. And I have a feeling for how big galaxies are because I study them, or I know how big they are with respect to stars or that kind of thing. So one way to understand scale is not to understand absolute scale and remember, okay, a galaxy cluster is 1 megaparsec across. It's just a fact, it doesn't mean anything. But understand the scale of something relative to the scale of something else. And we can work our way all the way back down to something that we all kind of understand. So we'll start with the Earth, okay? So how many of you have traveled, say, to a different continent outside of North America? Good fraction of you. Very, very good. Whether you're going south to South America or over to Europe or the other way around to Asia, in that flight, you've got a sense of the scale of the Earth. Now, you all have a feeling for how fast planes go. You've seen them before. You're riding on one. It takes a certain amount of time. You get a feel for the vastness of our planet. If you haven't done that, or even if you travel across the country in a plane or driven across the country, you get a sense of scale for at least that fraction. You can see the United States up there if you've driven across it. Well, you know, that's a good fraction of the diameter of the Earth. You get a feel for the size of the Earth. If you haven't done that, how many of you played with Google Earth? Okay, well, if you didn't raise your hand for either of those, you'll play with Google Earth. It's free. You can download it on your computer, and it's really cool. You know, you can zoom right into a building. These are pictures taken of the Earth from space. I probably don't have it loaded up on my laptop. We could play with it, but it would eat up too much time. But if you haven't played with it, go play with it. You can zoom into like your home and see it there. You know, if it was built before the last time the satellites flew over and imaged it. And then you can say hop over to wherever, San Francisco, and it will zoom out and you'll do this hop. It's kind of like a suborbital flight over the United States and down into whatever destination you give it. Through those hops and that motion, you can get a feel for the size of the Earth compared to objects that you have familiarity with, like buildings. Like you could find this building in Google Earth, zoom out, you see the city, zoom out, and zero in. Play with it a while, and you get a feel for how big the Earth is. Everyone feel like you have a good sense of the size of our planet? Okay. World's getting smaller, so, I mean, well, not literally, but everyone has more of a feel for the size of the planet than before, just because of ease of travel and communications and whatnot. Okay, so we'll use that as our starting point, at least in this step through. Now, the diameter of the Earth, the diameter is the distance across the circle, is 15,000 kilometers. Okay, so there's your base, 15,000 kilometers. Now let's go up to a larger scale. So what's this? Sun, good. You all passed the first test. So that's the sun. And you notice the scale there is 1,500,000 kilometers. Okay, so how many times bigger is the sun than the Earth? 100. Okay, yeah. Yeah, so you all know the answer. Say sun, and then I ask for a numerical thing. Yeah, it's 100. Yeah, just be bold with it. One thing I didn't mention last time, I don't think I mentioned last time, you're going to have to shout out your answers. You're going to have to just not be afraid, not be timid, because with the Ben's here, you can't hear him. The Ray might hear and just blocks out all noise. It's easy for you to hear me because I'm mic'd up, but you're going to have to shout out. Okay, 100. So let's see, a factor of 100. I can't reach, so I'll do it with the mouse here. So here's the sun. Okay, if we go, that's half a sun. That's a quarter sun. That's an eighth of a sun. 16th, 32nd, 64th. And another one would be, let's go a little bit less than another one. So that right there, from the edge of the sun to the left-hand side of my mouse, that's about 1/100th the sun. 1/100th the distance across. So that's really small. It's small kind of like some of these spots. These are bigger spots, but here's a little spot right there. What are these spots called? Sunspots, that's right. Yeah. Don't worry, the questions will get harder. So the Earth, our whole planet, is as big as this little spot here. Those spots, we talk about them a little bit. We'll talk about them more in Astro 102. They're just cold spots on the surface. Cold because the heat has to flow from the bottom up to the surface, and it's a complicated pathway for the heat to flow out. And sometimes magnetic fields get in the way and prevent the flow, the natural flow of hot to cold. And so you get spots that are merely 4,500 degrees instead of 5,800 degrees. If you were to look at just the spots, they'd be quite bright, but they're dim compared to the rest of the surface. Anyway, Earth is about the size of this cooled down region here. So that gives you a sense of scale for the sun or for a star. It's a pretty typical star. Stars range in size incredibly. Some can be as small as, well, it depends what kind of star you're talking about. If you talk about live stars, they could be, 10 times smaller than this, and they can also be hundreds of times bigger than this. Dead stars can get quite small. Some dead stars, white dwarfs, can be the size of Earth. Some, called neutron stars, can be the size of Chapel Hill. More massive than the sun, but compressed into the size of Chapel Hill. Those are neutron stars. And then you have black holes that are, that big, really small. Anyway, sizes of stars can range tremendously. This is a pretty typical one. Let's bounce up one more layer here. Actually, this is probably a couple steps. Going from the size of a star to the size of a galaxy. Now, is this our galaxy? No. I'm hearing probably nots and no's. And let me ask this. Why can it not be our galaxy? Can't take a picture of it. We can't get that far away from Earth. Not yet. Our most distant spacecraft is the Voyager spacecraft. They've now left the solar system. They're farther out than Pluto. But, our solar system is smaller than a pixel in this image. So we can't send spacecraft that far out and look back. So this is some other galaxy. There are lots of them out there to choose from. There are about 100 billion stars in our galaxy, and there are about 100 billion galaxies in the observable universe. It's a big, big, big place. But this is someone that probably looks a little bit like ours. It's spiral in shape. And its distance across in kilometers, now we're getting into crazy numbers. 1,000 quadrillion, which is a quintillion, so a quintillion kilometers. And we're in the range that, I don't know what a quintillion anything is like. I can't wrap my mind around a number that big. Maybe you can, but I can't. So astronomers define a new unit, one that's easier to manage. This one's called the light year. You can see it there. And our galaxy is about 100,000 light years across. So when we talk about hundreds of thousands of light years, you're thinking about galaxies. So let's spend a few minutes. I'll switch over and we'll make some notes here. And this will be about a light year. And this will be a good introduction to using some equations, some maths, unit conversions. Let's see if I can do this here. Let's turn it up. Okay. Go away, box. Go away, box. Okay. Good. It's a new dot cam. I'm not familiar with how it works, but we'll figure it out here. Yeah, okay, that works. So, okay, light year. So that light. I apologize for my handwriting. It's just horrible. Okay, so light year. What is the definition of light year? Yes, distance light travels in a year. And just, some of you are in there thinking, oh my God, this is so easy. It will get tougher. We're just going to start easy, do a few simple things. Everyone's on the same page here. Don't worry. I'll entertain you too. Okay, light year. Definition of light year is the distance light travels in 1 year. So this brings us to the equation that was up on, when I was showing the math notes last time, it popped up there. Distance equals speed times time. We're all familiar with this equation. If you're going on a trip and you want to figure out how fast you went, well, you'd have to solve it for, let's just do a little, we'll come back to this in a second. We'll talk about the different math skills that you would need last time. One of them is solving equations. So suppose you're going on a trip for 100 miles and it's taking you an hour. And so we want to figure out what our average speed was during that trip. Solve this equation for speed. We divide both sides by time. Yeah. So I'll just do that over here as an example. No, that's too far over. I do it right here. Distance is speed times time. The symbol for speed is v, velocity. I don't know why not s, but okay. Divide both sides by t, and then we have it solved. V is distance divided by t. That's an example of the level of math that you need to do. The equations will, of course, become more challenging and different and things you haven't seen before, but it's still basically isolating a variable and then it's plug and chug. And for the example that we just did, we said distance was 100 miles, and time is 1 hour, and so it's 100 miles per hour. So, going pretty fast. Okay. Distance is speed times time. Let's consider this in the context of a light year. Distance is 1 light year. I'll just use Ly for light year. The speed, so light travels at the speed of light, yeah. How many kilometers per second? 288, maybe 298? Okay, it's very close to 3. So we'll get it here in just a second, but yeah, it's very close to that. Times time, and the amount of time that we're talking about is 1 year. Okay, so that's a year. So let's write it down. I'm just going to round it off to the first digit. It's very close to 300,000 kilometers per second. So a little bit of scientific notation review. We can write this in scientific notation. So 3 times 10 to the... I got in kilometers per second at the moment, so that would be 5. Yeah. So what you do is 1, 2, 3, 4, 5, and the decimal point is here. That's 3.0 times 10 to the 5 kilometers per second. Or someone said times 10 to the 8, and that's in meters per second. I'll write them both here because we'll use them in both forms in this course. So 300,000 kilometers per second is 3 times 10 to the 5 kilometers per second, or 3 times 10 to the 8 meters per second. Let's just do an example of unit conversion, another aside. Mark these asides here. There's another aside. Unit conversion. Let's convert from one to the other. We have 3 times 10 to the 5 kilometers per second. If we want to convert that into meters per second, I like to use this chemistry format. You might have come across it in high school. It's really great because it helps you keep track of your units. If you're putting your units in there like you should, then you will multiply instead of divide, or divide instead of multiply. Well, you'll avoid that mistake. So we want to convert from kilometers to meters. In 1 kilometer, there are how many meters? 1,000, yeah? And so you then multiply 3 times 10 to the 5 times 1,000, which is 10 to the 3. Let's write that up here, 10 to the 3. So 3 times 10 to the 5 times 10 to the 3 is 3 times 10 to the 8. So it's going off the edge there, but it'd be 3 times 10 to the 8. And you check the units, the kilometers cancel with kilometers. If they don't cancel out, you did it upside down. You put your kilometers up here and your meters down there. Instead of multiplying by 1,000, you divide it by. But if you write your units here, you can cross them off, and you're left with 3 times 10 to the 8 meters per second. Yeah, you can also do that. Okay, so again, just an aside. I'm taking a long time to do this calculation, but I wanted to give you examples of the different things you're going to have to do in this course. Okay, distance is speed times time. We got the speed written out here in meters per second, or kilometers per second. Let's stick with that. Now we need 1 year. And what units do we need to get the year into? Seconds. We cancel the seconds right here. So, I wish I used more of my page here, but I'll do it on the next page and I'll come back and put it in. So 1 year, put my hash marks here so I know not to go any further. So 1 year, we need to convert to seconds. So let's use this chemistry format again. So in 1 year, we have how many days? Yeah, 365.242. Yeah. Don't worry about that. And in 1 day, we have 24 hours. You all know this. 1 hour, we have 60 minutes. In 1 minute, we have 60 seconds. And so, then you go and you check your units. Years cancel with years, day with day, hour with hour, minute with minute, and we're left with seconds. So we know we did everything right. Again, this one's an easy one, but it's good to run through a couple easy ones to make sure you know how to do it right. You're going to multiply everything across here and divide by each of these. And these are all 1. So divide by 1, divide by 1, divide by 1, divide by 1. It's not going to change anything. So you stick this into a calculator, and what you get is it's approximately pi times 10 to the 7 seconds. It's not exactly pi. It's like 3.15. But this is how I remember it. It's very close to pi times 10 to the 7 seconds in a year. The next time you're at a party and you want to impress your friends, no, don't do that. Okay. So let's put these together. Distance is speed times time. I'll just come back up here. And 3 times 10 to the 8 meters per second. There are kilometers. No, I'll come down here. Distance is 3 times 10 to the 5 kilometers per second times time, which is pi times 10 to the 7 seconds. And so 3 times pi is approximately 5? No, more. Yeah, it's, well, you know, 3 times 3 is 9, and to an astronomer that's 10. So, okay, this is something you got to understand. It's going to be different if you take a physics course or a chemistry course or something like that, where you're going to have to be really precise. But in astronomy, things are so hard to measure. They're not here in our laboratory. If we want to measure the distance of something far away, sometimes we're happy if we get it right within a factor of 2. Sometimes we're happy to know it to a factor of 10. So, you know, we're not going to worry about whether it's 9.9 or 10 often. Sometimes we have to, with atomic calculations and frequencies of light, but often we can just round off. So 3 times pi to an astronomer is 10. 10 to the 5 times 10 to the 7 is 10 to the 12. That's right, you add the exponents, and 10 times 10 to the 12 is 10 to the 13 kilometers. Okay, so we just did a lot of work, and what did we learn? 1 light year is 10 to the 13 kilometers. Does that help you? No, not really. I mean, I can't imagine 10 to the 13 of anything. What is that? It's 10 trillion. Yeah, it's 10 trillion. Oh, if you want to convert it to miles, you just multiply by 0.6. So this is 6 times 10 to the 12 miles. Anyway, it's a huge number, but one way to put it in perspective, the distance to the nearest star. So here we're talking astronomical stuff again. The nearest star is a star called Proxima Centauri. It's actually a triple system. Alpha Centauri is the bright one. There's another star going around it really close and one going around it pretty far away. That one is technically the closest of the 3 to us, but they're all about the same distance, and that's 4.3 light years. So when I'm talking about light years, the comparable astronomical thing would be the distances between stars in our neck of the galaxy. Stars tend to be a few light years apart. Sometimes they're closer, sometimes they're farther, but at least it gives it some context. So another way to think about this is the light, if you go out and take a look at Alpha Centauri, you're seeing it as it was 4.3 years ago. It took 4.3 years for the light to get to us. Even though light travels really, really fast, the universe is really, really big, so time takes a lot of time for light to get from one place to another. That's, again, full of asides here today, but that's one of the really cool things about astronomy. The farther out we look, we're looking into the past, because it takes time for the light to get to us. You know, other fields like archaeology, you dig down in the earth, you find a site, but you're seeing it as it is today. It's a big mess, and you're trying to piece together the story. In astronomy, if we want to know what happened in the past, we just have to look farther away, build bigger and better telescopes and instrumentation, look farther away, and we're seeing it as it was in the past. We can look back billions of years and just see the history occurring. That's kind of the cool thing about astronomy. It's a bit of a time machine at the same time. But a lot of that would be 102 material. 101, we're not going to go so far away. Sometimes we will. Okay, nearest star, 4.3 light years. Okay, so back to our, let me switch. Oh, questions about that? Any questions about those calculations, unit conversions? Yeah, we got one back here. That's right. The only thing that we know is presently happening is what, you know, like right now I'm looking at you, but I'm looking at you some fraction of a microsecond ago. Yeah? Yeah, absolutely. So the question, sorry, I'm having a conversation here and you all can't hear. When we look out, we can't see it as it is now unless it's like really close to us, like Alpha Centauri. 4 years ago is now when you're talking about cosmological timescales. The universe is 13.7 billion years old, so a couple of years is kind of the present. But we can't see the universe as it is now except in our neck of the woods. as you pointed out, we could see a star. That star might be gone. We see a star explode. It actually exploded thousands of years ago, that kind of thing, or millions or billions. Personal story, relates to my research on the subject of exploding star that's not there anymore. In 2005, my research group, an undergrad actually, with me discovered the most distant explosion in the universe. It occurred 12.8 billion years ago. The universe is 13.7, so we're like 94% of the way back. So that star lived its life, it exploded, made this huge burst of radiation, started traveling across the universe. The sun formed, Earth formed, life started to evolve, travel across the universe. Eventually humans evolved, we built telescopes, pointed them in the right direction and captured the light. So, yeah, it's long, long gone. That undergrad, by the way, got to be first author on the publication in Nature for his discovery, so that's not shabby for an undergrad. Okay, let's go up. Any other questions? We'll go up one more. Let me switch this back to the laptop. Okay, one more level up. So here we're talking about a galaxy, 100,000 light years across. And again, I should say, just like stars, there are big galaxies, there are small galaxies. There's a wide range. A galaxy like our Milky Way galaxy is about 100,000 light years across. There are baby galaxies, dwarf galaxies we call them, that orbit us. And there are certainly bigger galaxies out there in the universe too, cannibalistic ones that gobble up other galaxies. And this is kind of related to that, not by intention, but here we are one level up, going from 100,000 light years to 1,000,000 light years. You can see clusters of galaxies, or groupings. This would probably just be a group of galaxies, but the groups group, and we call those clusters, and the clusters cluster, and we call those superclusters. But here, once you get up to about 1,000,000 light years, you're on the scale in which galaxies are clumping together due to their mutual gravitational attraction. And it's a little different from stars. The distances between stars are enormous compared to the size of the stars. So the distance between galaxies is only about 10 times the size of the galaxy. Galaxies can run into each other. Stars, they never, except under some pretty extreme circumstances. The stars never really run into each other. They can pass by each other, get close gravitationally, maybe get close enough to disrupt the planets that are orbiting each star. The galaxies, they run into each other. It happens quite a lot. In fact, that's how you get big galaxies. Little ones collide and merge and grab more. And some get really big. Those are the cannibalistic galaxies. So they tend to be tightly packed compared to their size. So that gets us up to the scale of galaxies or small groupings of galaxies. Here's another slide. Kind of the same thing, just different steps. I'll just go through it real quick so you have some more numbers to start getting into your intuition. This one starts with the Hubble Space Telescope, which I don't know why they do that, but here's an astronaut's for scale. The Hubble Space Telescope is about the size of the Space Shuttle cargo bay, because it went up in the Space Shuttle cargo bay. In fact, there's Space Shuttle cargo bay. Yeah. Okay, and about 500,000 times bigger than the Space Shuttle is the Earth. That's not a very useful transition. But here's our Earth again. If we go a factor of 1,000,000 from the Earth, we get to the size of our solar system. And so, the other planets are kind of small, like, some are bigger than the Earth, like Jupiter and Saturn, but they're not 1,000,000 times bigger. The solar system is mostly empty space, with a few little bodies going around the sun. The sun is even small compared to it. Again, the sun is 100 times bigger than the Earth. The solar system is 1,000,000 times bigger than the Earth. So the solar system is mostly empty space. Go up another factor of 10,000. That's our local neighborhood of stars, the gravitationally interacting stars around us. Another factor of 15,000 or so gets you up to the galaxy. Another factor of 10 or 20 gets us up to the local grouping of galaxies. Another factor of 200, 300 or so gets us up into the large-scale structure of the universe, the cosmic web. Draw all the galaxies and gas and how they're gravitationally attracting on the largest scales imaginable. And that gets us into cosmology. Again, just a few extra steps in this slide. I figured it's good to throw up another example. Okay, any questions about size and scale?